So I'm pleased to introduce Chen Liang for this presentation. Chen Liang is a PhD student at Georgia Tech, and she has done a lot of great work in making neural language models more generalizable and more efficient. And today she's going to talk about some of her ongoing and kind of accomplished work on parameter efficiency of neural language models. So yeah, Chen Liang. Please take it away.
Okay, thanks, Hannah, for introducing me. I'm very happy today to share some of my previous work on improving parameter efficiency of neural language models. And this talk will mainly cover three directions. One direction is to develop training algorithms for improving parameter utilization and model generalizability. And the second direction is to develop pruning and knowledge distillation algorithms for model compression. And in the third part, I will introduce the parameter efficient learning schedule. And please feel free to interrupt me if you have any questions. First, I want to motivate this talk by discussing why do we care about parameter efficiency and redundancy in neural language models. In recent years, the pre-trained language models has grown to contain up to hundreds of billions of parameters. And the recent work have shown that models with billion-scale parameters give rise to remarkable capabilities such as zero and few-shot generalizability on unseen tasks. For example, one recent work shows that different types of large language models exhibit a consistent surge in accuracy of zero-shot and few-shot accuracy on different types of unseen tasks. For example, reasoning, arithmetic, question answering, and summarization, and etc. But despite their remarkable generalizability on unseen tasks, it's very challenging to using those large language models on downstream tasks because large models incur prohibitive computational and memory costs, making them difficult to be deployed in applications with latency and storage requirements, such as chatbot, search engine, and mobile gaming. In fact, recent work have shown that there exists a significant proportion of redundant parameters in pre-trained language models when they're being fine-tuned or adapted to downstream tasks. This figure shows the evaluation accuracy of different pre-trained language models when being fine-tuned on the GLUE benchmark, which is widely used the natural language understanding benchmark, versus the number of parameters in those models. And we can see that further increasing the model size only yield marginal gains. For example, further increasing the size of the T5-3B model by nearly 4 times will only give rise to less than 2 points of gain on the GLUE benchmark. This suggests that we're losing the parameter efficiency, and there exists a significant redundancy in pre-trained language models. To better understand and analyze the redundancy in pre-trained language models, existing researchers have proposed a metric called sensitivity score to evaluate the redundancy of each individual parameters in the model. So sensitivity of a parameter approximates the difference of the loss function when replacing this parameter with 0. The definition of sensitivity is shown in the equation below. Here, the I sub j denotes the sensitivity of the jth parameter, and is computed as the magnitude of the weight gradient product. Here, the theta sub j denotes the jth parameter, and L denotes the loss function. And this definition is derived from the first-order Taylor expansion of the loss function with respect to theta sub j at theta. Here, the theta backslash j denotes the model parameter theta with the jth parameter being replaced with 0. So based on this definition, we know that a small sensitivity indicates that the weight is not very important or redundant because the removal of such a parameter will not cause a large influence to the model loss anyway. So the sensitivity score is often used as an importance metric for weight pruning in the literature. In weight pruning, we want to remove the most redundant sets of parameters or the most redundant connections between neurons from a dense model. And the resulting model will be a sparse model that is more computationally and memory efficient. And weight pruning technique has been shown to be effective for neural language models. Recent work has shown that removing the redundant parameters can greatly reduce the model size at a very small expense of performance drop. And furthermore, one of my previous work have shown that removing the redundant parameters can not only retain a comparable performance to the full model, but can even improve the performance to the downstream task. So the figure here shows the evaluation accuracy of the pruned BERT-based and BERT-large model after they're being fine-tuned on the RT dataset, which is a textual entailment dataset. The x-axis here shows the proportion of the remaining weights in the pruned model. And the blue, orange, and green curve each represents the accuracy of the model after pruning the most redundant weights, the random weights, and the most important weights. And we can see that by removing the most 20 to 30% of the most redundant weights from the model, the pruned model can actually achieve a better performance, generalization performance than the full model. And we call this first increase and then decrease behavior as the phase transition phenomenon. And this suggests that removing the redundant parameters can even improve the model generalizability on the downstream task, in addition to its practical benefits, such as memory and computational efficiency. So this drives us to ask the question that how to improve the parameter efficiency of neural language models. So in the first part, I will introduce a sensitivity-aware optimization algorithms to improve the parameter utilization and promote the training of the redundant parameters. Recall that a small sensitivity indicates that the weight is not very important or redundant. So can we improve the training of the weights with low sensitivities so that they can be less redundant and finally contribute to the model performance? The initial algorithm we came up with is an adaptive learning rate schedule, where we assign a different learning rate to individual parameters based on their sensitivity score. Specifically, at the tth iteration, we compute the adaptive learning rate for the jth parameter as eta sub j, which is computed as the base learning rate times 1 over the sensitivity score of the jth parameter. And then we update the jth parameter via one gradient descent step using the newly assigned learning rate. The motivation for such a formulation is that since we consider the weights with smaller sensitivity scores to be insufficiently trained, we want to assign them a larger learning rates to promote their training to encourage their exploration. However, this algorithm fails to converge. And we later find that the cause of such failure is that the sensitivity scores are quite noisy. The figure here shows the variance of the sensitivity score across training iterations for the weights randomly selected from 12 layers of a BERT model fine-tuned for the RT dataset. And we can see that the variance of the sensitivity spans order of magnitude. And we suspect that the uncertainty in the sensitivity scores mainly come from two sources. One is that the sensitivity score is computed using the magnitude of the gradient weight product, and the gradients are actually the stochastic gradient with respect to each mini batch. So the gradient itself is very noisy, causing uncertainty in the sensitivity score metric. And secondly, the training dynamics for fine-tuning a large model could be quite complicated. So the value of the weights and the gradients can drastically change across iterations, which also cause fluctuation in the sensitivity scores. So in order to take into consideration of the uncertainty of the sensitivity, we keep track of the statistics of the sensitivity. Specifically, we compute the exponential moving average of the sensitivity across iterations. And we quantify the uncertainty of the sensitivity as the absolute difference between the current sensitivity and the exponential moving average of the sensitivity. So essentially, a large uncertainty means that the current sensitivity deviates significantly from its historical mean, which means that the current sensitivity may not be a reliable indicator of redundancy for the J's parameter at the current iteration. And finally, we propose SAGE, a sensitivity-aware learning rate schedule. And it's computed as the base learning rate times the uncertainty of the sensitivity over the sensitivity itself. A smaller sensitivity will encourage a larger learning rate, and this is to promote the training of the redundant weights and also to regularize the training of the overfitted weights. And the larger uncertainty will encourage a larger learning rate. And this is to encourage the exploration of the weights with unreliable sensitivity scores. So this is essentially a trade-off between exploitation and exploration. And we evaluate the proposed sensitivity-aware learning rate schedule by fine-tuning BERT-based and the Roberta large model on the glue benchmark, and also fine-tuning the VIT model on the CIFA 100 and ImageNet dataset. And we can see that SAGE can achieve a consistent improvement over all different tasks and data sets in both image and text domains. And it can be combined with different optimizers such as ADAM and SGD, and is complementary to existing strong regularization technique for fine-tuning pruning language models, such as SMART. And worth noticing, on BERT-based, which is a model that is well known for its undertrained, SAGE can improve 2.5 point of gain, and which suggests that SAGE can better fit the BERT-based model on the downstream task. And here we visualize and compare the training loss, validation loss, and learning rates between SAGE and ADA. And we can see that under the same learning rate scale with ADA and SAGE can yield a lower validation loss. And this suggests that by promoting the training of the redundant weights and also regularize the training of the overfitted weights, SAGE is able to encourage a more balanced training across all parameters, which yields a regularization effect and improves the model generalizability. And we also visualize the accuracy of the pruned model that is fine-tuned with ADAM and fine-tuned with SAGE. And we can see that when pruning the model that is fine-tuned with SAGE, which is shown in this orange curve, the phase transition phenomenon becomes less obvious, which suggests that even the most redundant parameters in the model can contribute to the model performance. So pruning them will cause no good benefit to the model performance. And further suggests that SAGE can encourage a more balanced training across all parameters. And as an extension of this work, in the part 2, I will introduce an uncertainty-aware pruning algorithm, where we propose a new importance score by taking into uncertainty of the sensitivity score. In this setting, we consider the iterative pruning setting, where the model is gradually pruned throughout the training process towards the target sparsity. And at the Tth iteration, we will take one gradient descent step to update the model parameter, and then prune the model parameter based on the sensitivity score. And the pruning operator is defined as the following, where we will retain the J's parameter if its sensitivity is among the top RT% of the sensitivity score for all parameters. And the J's parameter will be pruned otherwise. Here, the RT will follow some decaying schedule. So at the end of the training, the RT will be equal to the target sparsity. Similarly, we keep track of the exponential moving average of the sensitivity and quantify the uncertainty of the sensitivity as the absolute difference between the current sensitivity and its historical mean. And we further compute the moving average for the uncertainty score to further stabilize this measure. And finally, we propose Platen, a new important score for weight pruning, which is computed as the product between the sensitivity score and the uncertainty of the sensitivity. Since a larger uncertainty means that the J's parameter's sensitivity is not yet a reliable indicator for the J's parameter. And therefore, we want to retain the J's parameter for further training and exploration by increasing its importance score. So in this way, we can avoid incorrectly prune some important weights that happen to have small sensitivity at the current iteration due to the large uncertainty. And we evaluate this pruning importance score by pruning the bird-based model on the glue benchmark and the squat benchmark. The squat benchmark is a question answering benchmark that is also widely used. And we prune the bird-based model towards 20% and 10% of its original size. So this is a highly sparse region, which is very challenging. And we can see that Platen can achieve a consistent improvement over all different tasks and different pruning ratios upon the strongest iterative pruning baseline, the soft movement pruning. And here is a visualization of the evaluation accuracy of the pruned bird-based model under different pruning ratios. And we can see that in the blue curve, which represents the accuracy of Platen, we can see that it's achieved a consistent improvement over different pruning ratios. And the gain is very prominent at very sparse region, which suggests that by retaining the weights with great potential, it can achieve a very reliable pruning towards high sparsity region. Okay, so in the third part, I will introduce two knowledge gap aware distillation algorithms for task specific and task agnostic model compression. In knowledge distillation, we transfer the knowledge from a large pre-trained teacher model to a small student model. And in knowledge distillation, we want to train the student model to match its output prediction distribution to that of the teacher model. So the training objective of knowledge distillation mainly consists of two terms. The first term is the task-specific loss. For example, it could be the cross-entropy loss for classification task. And the second term is the knowledge distillation loss, which often takes the form of the KL divergence between the prediction distribution of the student and the teacher model at the final layer. However, knowledge distillation ignores the rich contextual and semantic knowledge at the intermediate layer. So existing researchers have also proposed a layer-wise distillation approach, where they train the student model to match the hidden representation at each of its layers to the hidden representation at the corresponding layers in the teacher model. So the training objective of layer-wise distillation consists of a layer-wise distillation loss, which is computed as the sum of the mean squared error distance between the hidden representation at all layers of the student model and the hidden representation at the corresponding set of layers in the teacher model. Here we consider a predetermined one-to-one teacher-to-student mapping, layer mapping. For example, we map the case layer of the student to I subcase layer of the teacher. However, layer-wise distillation is very challenging due to the large knowledge gap between the teacher and student model. The capacity of the teacher model is significantly larger than the student, so there can be large discrepancies between the hidden layer representations of the teacher and student model. And the students may struggle to mimic the teacher's representations over massive training data and become underfitted. So here we show the training loss during the distillation between a 6-layer GPT-2 student and a 12-layer GPT-2 teacher on the open web text dataset. And we can see that the training loss under the layer-wise distillation loss, which is depicted in this blue curve, converges slower and it remains higher than the training loss under the knowledge distillation objective. And this suggests that the layer-wise distillation, under layer-wise distillation, the students can be underfit to the training dataset, and layer-wise distillation fails to facilitate an effective knowledge transfer. So in order to reduce the knowledge gap between the teacher and student model, we propose a task-aware filtering approach. The high-level idea is to only select the knowledge that is relevant to the target task from the teacher to distill to the student model. The motivation is that since the teacher model is pre-trained on the open domain data, so not all knowledge in the teacher model is useful for the target task learning. Since we mainly care about the student performance on a specific target task, then it is not necessary for us to enforce the student to perfectly mimic all hidden layer representations of the teacher model. So in order to select the knowledge that is useful for the target task, we equip each layer with a equip each layer of the teacher and the student model with a task-aware filter and a task-specific head. And this task-aware filter is a learnable linear projection, and the task-specific head can be a linear softmax layer for classification. And we expect that after training such filter based on the task-specific prediction objective, the filter is able to learn to extract the knowledge that is useful for the target task prediction. And to achieve this goal, we propose a two-stage framework. In the first stage, we freeze the teacher and student model and learn the task-aware filters. Specifically, given a properly initialized teacher, we denote the case filter as G parameterized by W sub K. This filter will take in the hidden representation at the corresponding layer and output a filtered hidden representation. And the task-specific head will take in the filtered representation and compute a task-specific prediction loss. And after we compute the task-specific losses for all filters, we will freeze the model and jointly optimize all filters. And in this way, the filters can learn to select the knowledge that is useful for the target task prediction. And in the second stage, we conduct a task-aware distillation on the filtered output representations. Specifically, we fix the teacher model and its filters and optimize the student model and its filters to align their filtered output representations. The task-aware distillation loss is computed as the sum of the mean squared error between the outputs of the student filters at all layers and the output of the teacher filters at all layers, at the corresponding set of layers. And then the layer-wise distillation objective, the task-aware distillation objective, is very similar to layer-wise objective, but except that we're replacing the layer-wise loss with the task-aware loss. And since we know that the filtered representations contain the knowledge that is useful to the target task, so by minimizing the task-aware distillation loss, we only encourage the student model to mimic the useful knowledge, which makes distillation much easier and more effective. And we evaluate our task-aware distillation approach on language modeling and natural language understanding benchmark. For a language modeling task, we consider a GPT-2, a 12-layer GPT-2 model as the teacher model, and then we distill a 6-layer GPT-2 as the student model on the open web text dataset. And we evaluate the distilled students with zero-shot and transfer learning setting on the Wikitext 103 and the Lambda dataset. And for the NLU benchmark, we consider using a 12-layer Diberta V3 base teacher and to distill a 12-layer Diberta V3 X small as a student. The student model is thinner than the teacher model, where the teacher model has a hidden dimension of 768, and the student has a dimension of 384. Yes. And we can see that the task-aware distillation can achieve a consistent improvement upon different tasks and data sets on both the language modeling and the NLU benchmark. And we can also observe that the layer-wise distillation not always gives an improvement upon the knowledge distillation, vanilla knowledge distillation baseline due to the large knowledge gap issue. But the task-aware distillation can improve upon both the vanilla knowledge distillation and layer-wise distillation baselines. And here we visualize the training loss and layer average distillation loss for task-aware distillation. And we can see that the training loss under the task-aware distillation objective, which is shown in this orange curve, can converge faster and remains lower than the knowledge distillation and layer-wise distillation objective, which suggests that the students under task-aware distillation can better fit to the training data. And also, the layer average distillation loss in task-aware distillation is much lower than layer-wise distillation loss. This suggests that the discrepancy between the filtered output representation is much smaller than the unfiltered representation, which suggests that the filter can effectively select the knowledge that is useful to the target task and make distillation easier and reduce the knowledge gap. However, such a task-aware knowledge selection idea is mainly designed to resolve the knowledge gap issue in task-specific distillation, where we only require the student to perform well on a specific target task. While a more challenging setting is task-agnostic distillation, where we want to distill a student to be a pre-trained model, which can be easily adapted to any task. The knowledge gap issue is also prominent in task-agnostic setting, but the knowledge selection idea may not be effective because the target task can be arbitrary and all knowledge can be relevant, so making this setting more challenging. So to maintain a small knowledge gap in the task-agnostic setting, we propose a homotopic distillation method. Specifically, we initialize the student model from the teacher model and iteratively prune the student throughout the distillation process until the target width is reached. By initializing the student from the teacher, we're able to maintain a small discrepancy at the early stage of training and facilitate an effective knowledge transfer. And at the future training iteration, we will first prune a very small set of most redundant neurons from the student, which will give rise to a small increment in the teacher-student discrepancy. And then we will conduct one distillation step by optimizing the student model using the layer-wise distillation and knowledge distillation laws, so that such an increment in the discrepancy can be further reduced. And in this way, we're able to maintain a small discrepancy throughout the training process. So here is a visualization of the prediction discrepancy between teacher and student throughout the distillation process. Here, the T sub f denotes the number of iterations to achieve the target width in pruning. And the capital T denotes the total number of iterations in the distillation process. And by setting T sub f to 0, directly reduce homotopic distillation to the standard distillation. So this blue curve represents the prediction discrepancy in standard distillation, while the bottom three curve represents the prediction discrepancy in homotopic distillation, under different pruning schedules. We can see that the prediction discrepancy starts off at a very large point in standard distillation because we initialize a small student outside of the teacher model, maybe from a random point. While in a homotopic distillation, we initialize a student from the teacher, so the discrepancy is very small at the beginning. And while we iteratively prune the student model, the discrepancy gradually increases, but remains to be small because we simultaneously distill the student model and maintain a small knowledge gap throughout the whole distillation process. And we evaluate the homotopic distillation method by prune a bird-based model as a teacher into 4 different scales of student homobird student model. And we consider 60 million parameter scale students and 15 million parameter scale student. And we distill the students in a continual pre-training setting where we use the Wikipedia and book corpus, which are the pre-training corpus for BERT model. And this figure shows the evaluation accuracy of fine-tuning the distilled students on the blue benchmark. And we can see that at the 60 million parameter scale, our homobird students can achieve comparable performance to the state-of-the-art method. While at the 20 million parameter scale, our homobird students can achieve a significantly better performance than existing task-agnostic distillation method. And the observation is also consistent on the squad benchmark, where we show that at the 15 million parameter scales, our homobird students can achieve a significantly better performance than existing task-agnostic baselines. And in the last part, I will introduce a task generalizable parameter-efficient fine-tuning method. We know that parameter-efficient fine-tuning, or PFT, considers adding a minimal set of parameters to the pre-trained model and only fine-tune those parameters. And existing PFT methods includes prefix tuning, low-rank adaptation method, and adapter method, and etc. The benefits of using PFT methods is that the PFT methods can effectively adapt a pre-trained model to specific tasks, as in traditional fine-tuning, while at the same time, it can save the storage cost by only saving the minimal set of added parameters. However, PFT methods also inherit the disadvantage of traditional fine-tuning, which is that the adaptation to each new task requires a new round of fine-tuning, which induces substantial computational cost and resulting in poor task scalability. On the other hand, in-context learning, or ICL, has been recently proposed to improve the generalizability of the pre-trained model to the unseen task without any fine-tuning cost. So in context learning, we can directly inference a pre-trained model on any unseen task by conditioning on some few-shot demonstration examples from this task. As shown in this illustration, for any unseen task, we can collect some few-shot demonstration input-output pairs and format them with task-specific instructions or prompts. And the pre-trained model can take in the concatenation of those few-shot demonstrations and the actual query to generate the response to the actual query. While in-context learning can generalize to unseen tasks without any fine-tuning cost, it also has the disadvantage of lacking the adaptability to specific tasks because a single pre-trained model is used for different tasks without any parameter adaptation. So hypernetwork approach has been proposed to achieve efficient generalizability to unseen tasks and at the same time to achieve effective adaptation to specific tasks. As shown in this illustration, for any unseen task, the hypernetwork is a meta model which takes in the few-shot demonstration examples from this task and generates PFT parameters for this task. And the pre-trained model will then use the generated parameters to inference on the unsynced task. So the hypernetwork approach can be generalized to unsynced tasks because they can generate the PFT parameters with a single forward pass instead of learning the PFT parameters via iterative fine-tuning. And secondly, hypernetwork is adaptable to specific tasks because the parameter it generated is task-specific based on each task-specific demonstration examples. So in order to train this kind of meta model type of hypernetwork, existing work proposed a hypertuning approach, which multitask train the hypernetwork on a large collection of diverse NLP tasks. Specifically, we consider encoder-decoder transformer type hypernetwork, denoted as H parameterized by Xi. At the Tth iteration, the hypernetwork decoder will take in a learnable token Z and generates a hidden state H via one decoding step. Noted that the generation will be conditioned on E, which is the encoded representation of the few-shot demonstrations. So essentially, the hypernetwork is a conditional text-to-weight generator. And then we will learn LMLP layers to project this shared hidden state to L set of PFT parameters, where this phi sub L is the set of parameters generated for the Lth layer of the pre-trained model, denoted as M parameterized by theta. And the hypernetwork is then optimized based on the prediction loss of the pre-trained model. And notice that here the pre-trained model is parameterized by theta and also the newly generated PFT parameters phi. And when we optimize the hypernetwork, we will keep all the weights in the pre-trained model frozen. However, the current hypertuning approach has several limitations. One limitation is that the parameter generation scheme has low sample efficiency because the current generation only relies on the MLP layers to learn the parameters at different layers of the MIM model, while underutilize the transformer decoder, which is more capable of capturing the layer specificity for high-dimensional weight spaces. And secondly, we observe that the PFT parameters at different layers of the MIM model actually exhibit highly structural dependency between neighboring layers. Specifically, we found that the PFT parameters at one layer is highly dependent on the PFT parameters at its previous layer, while MLPs cannot exploit this underlying problem structure. And the second limitation is that the training of such hypernetwork is very unstable. This is because the few-shot demonstration examples can be highly diverse. So the PFT parameters that is generated based on the demonstration examples can exhibit high variance across iterations, which further causing variance in the prediction loss and gradients. To resolve these two limitations, we propose two strategies. The first strategy is the autoregressive parameter generation. At the Tth iteration, we want the hypernetwork decoder to generate a sequence of L hidden states autoregressively while L decoding step. So at the first decoding step, the hypernetwork decoder will take in a learnable token Z and generate the hidden states for the first decoding step, H sub 1. And in the else decoding step, the decoder will take in the hidden states generated at the previous decoding step as the input to generate the hidden states at the current decoding step. And after we learn LMLP layers to project the, after we learn this L hidden states, we then learn LMLPs to project those states to L setup PFT parameters. And so the motivation for such an autoregressive parameter generation is that we can leverage the transformer decoder to capture the layer specificity of the parameters at each layer. And the second motivation is that we can adopt the autoregressive decoding scheme to exploit the underlying problem structure, the structural dependency between neighboring layers, and introducing proper inductive bias into the generation scheme. And by using this autoregressive parameter generation, we're able to generate more expressive PFT parameters that have higher representation power to fit the pre-trained model to the downstream task. And the second strategy we propose is called local consistency regularization. And specifically at the tth iteration, we will compute the local consistency loss as the mean squared error between the sequence of hidden state generated at the current training iteration and the sequence of hidden states that generated at the previous training iteration. And finally, we will optimize the hypernetwork based on the sum of the prediction loss and this local consistency loss. The motivation for designing such a local consistency regularization is to encourage the consistency between the generated parameters at the consecutive iterations. So in this way, we can avoid drastic change in the generated parameters, as well as to avoid the drastic change in the prediction loss and gradients of the hypernetwork. Since this is an ongoing work, I will going to show some preliminary results on this work. So we evaluate the method on the supernatural instruction data set. The supernatural instruction data set is a large-scale collection of tasks, including 1,600 more tasks for instruction fine-tuning. And we train the hypernetwork using multitask instruction fine-tuning with few-shot examples. And we test the pre-trained model on the held out unseen task of supernatural instruction dataset to test the hypernetwork generalizability. And we evaluate the method on T5 large and T5 3B model. So we initialize both the hypernetwork and the pre-trained model using the T5 large or using the T5 3B model. And we can see that by comparing with existing PFT methods like prefix tuning and LoRa, as well as the recently proposed hypertuning method, our method can achieve a nearly 2 points of gain on top of hypertuning. And very interestingly, when we're replacing the hypernetwork, the T5 large hypernetwork with a FLAN T5 large hypernetwork, which is a more powerful hypernetwork, we're able to boost the performance by 3 points, which suggests that by using a more powerful hypernetwork, we're able to search better fitted PFT parameters for the downstream model, for the pre-trained model. And finally, I show an ablation study for the two strategies that we proposed. And here we also evaluate on the P3 dataset, which is a public pool of prompts. It's a large-scale collection of tasks for prompted fine-tuning. And we can see that on both the supernatural instruction and P3 dataset, the autoregressive parameter generation gives around 1.3 points of gain, and the local consistency regularization gives another 0.5 points of gain. And here we show the training loss of the model trained on supernatural instruction dataset and P3 dataset with and without using the autoregressive parameter generation. And we can see that the model trained with autoregressive parameter generation can yield a lower prediction loss during the training process. This suggests that the PFT parameter generated can better fit the training sets, and can so the hypernetwork is able to produce more and search for more expressive PFT parameters to fit the downstream task. And that's mainly conclude my talk. And here are some take-home messages. First, there exists a significant redundancy in neural language models, and sensitivity-aware optimization reduces the parameter redundancy. And uncertainty-aware importance score can improve the reliability of the weight pruning. And task-aware distillation reduces the undesired bias by ignoring the redundant, task-irrelevant knowledge. And homotopic distillation maintains a small knowledge gap in the task-agnostic distillation. And autoregressive parameter generation can improve the representation power of the generated parameters. And that concludes my talk. So thank you. I would like to take any questions if you have. Thank you for taking the time to attend my talk. Thanks.
Thank you. This is great. So any questions?
I have a couple of questions.
Okay.
I am also so just for context, I'm working in the domain of compression here right now. So I had a couple of questions. First one regarding the homotopic distillation paper you mentioned.
Yes.
And what the setup you did for the next work, which was, I guess, the in-context learning thing. So did you try and run the homotopic distillation baselines for your in-context learning pruning setup?
In which in-context learning pruning setup?
Oh, the next paper that you mentioned, for larger models like T5, you have parameter efficient fine-tuning and then in-context learning things. So you went to solve that problem, you resorted to hypernetworks. So my question is, did you try to run the task agnostic homotopic distillation baselines for the other setup instead of going hypernetworks?
So if I understand correctly, you ask if I have compared with the students that a homotopic distilled students using in-context learning tasks and data sets, right?
Yes. Yes.
Okay. So for a homotopic distillation, we consider in a continual pre-training setting. So the distilled model will be a pre-trained model, and we mainly evaluate this distilled pre-trained model on the fine-tuning data set. So we fine-tune the model on the glue benchmark and on the squat benchmark, but we haven't tested on few shot, zero shot, or in-context learning setting. But it will be interesting to see if such distillation works for in-context learning setting. We have to try this method on larger models in order for the distilled model to work on in-context learning setting, because I think the currently we'll only distill a BERT model. So I don't think the distilled student can work well in terms of zero shot and in few shot generalization.
Do you have any prediction in terms of performance or efficiency on how this method will scale up with data or model size?
You mean in terms of the inference speed? And so this method mainly distill the width of the model. So as you can see from this figure, we're mainly considering reduce the size of the matrix of the model. So it does give an inference speed up, depends on the target sparsity that you want. It can give an inference speed up of 2 to 3 times. For example, in our case, we consider 110 to 15 million parameter scales. This will give a speed up of 2 to 3 times in terms of inference. And for training, for the distillation itself, we will consider a continual pre-training setting. So it will be the training time will be less than the original pre-training setting because we have an already pre-trained model as the teacher, so that we don't need to like pre-train the student from scratch. But I do think it will still require a partial like pre-training time, like several. For example, if the pre-trained model is trained using 2 to 3 trillions of tokens, I would suspect that the distillation will requires 0.5 to 0.3 trillions of tokens. Yes.
Okay, yeah, that's quite a bit.
Mm-hmm.
Yeah. And my second question is actually related to the Platin method that you mentioned. I think from what I understood, it is only for pruning individual parameters of a network, like in an
Yes.
unstructured setting. Do you think this will, like the same pruning criterion will generalize to bigger structured blocks? The only reason I ask this is because unstructured pruning, even though it gives you the best performance, it doesn't give you any speed up on hardware because of the unstructured nature. So the next obvious step would be to take the pruning criteria that you have and see if it works for bigger attention blocks or stuff like that.
Yes, we actually conduct a structure pruning setting for the Platin, and it's shown in the paper, but I didn't present here. So we consider prune the neurons, like the rows and columns in the matrices specifically. So Platin also shows improvement upon existing iterative pruning baselines in the structure pruning setting.
Yeah, thank you so much for answering my questions.
Mm-hmm.
More questions?
I have a question about the first part of your talk. Thanks for the great talk, by the way. There's lots of interesting information here. For the sensitivity-aware optimization stuff, you defined your sensitivity score in terms of how much the loss would change if you zeroed out a specific parameter, right? If I understand.
Yes.
But you're using the sensitivity scores during training, right? I mean, it kind of makes sense when you reason about how important a specific parameter was after you've trained the model. But how reliable are these scores, I guess maybe intuitively, during training itself, when things could change a lot during training?
So this sensitivity score has been widely used during iterative pruning. So I don't quite, I'm not quite sure, like your question is like whether the sensitivity score is the meaning of the sensitivity score differs when the model finished training and during training. Is that your question, or?
Yeah, right. So after you've trained the model, you can reason about whether or not a specific parameter is useful, right? I mean, you can zero it out and check whether the loss changes.
Yes.
But during training, I mean, even before you take a specific gradient step, how do you make that kind of a decision?
Oh, okay, I see your question.
Yeah.
So I think I show the computation here. So the most accurate approximation, the most accurate computation for this sensitivity should be like a zero out a parameter and then compute the loss difference. But during training, we can't do this. Like we cannot like zero out each individual parameter. That will be time consuming. So we do like a first order Taylor expansion, and we approximate the sensitivity at the weight gradient product. So like at each iteration, we only need to compute the value of the weight and the gradient of the weight, like element-wise, to achieve its sensitivity score.
Yeah, my question was not necessarily about the efficiency, which I think is also important. But Yeah, I guess when I'll ask you this question again when we meet one-on-one. Maybe one other quick question. How does this generally compare with sharpness-aware minimization?
The sharpness-aware minimization, I think those are for robustness. So that method is mainly to suppress the sensitivity for suppress the parameter that was high sensitivity so that they can be less sensitive to perturbations. So I think the purpose of that work is different from ours. Ours is to promote the sensitivity for less sensitive neurons, and this is to like improve our generalizability and also fitting on the training set. And for that work, that work is to improve the robustness of the model by suppress all the sensitive parameters. That's my understanding.
Okay, cool. Thanks.
Thank you. We might have time for one more question, or we are almost at 11. That's good. Thank you, Chen. It was a great talk. So I have some detailed question that I can ask you in our one-on-one. It's more than 1 minute. So I'm guessing others too. So we'll chat later.
Okay.
Thank you.
Thank you. Thank you so much.